Okay, hello everyone. I see that at least 10 people starting together with us. Here at this call we have Łukasz and Piotr. Today's today's meetup will be split for 2 days. Today we will listen a supervised part, and then April 30 we will listen unsupervised part. So let me introduce Łukasz. He will be our first speaker for today, and so we will hear him very soon. So welcome everyone to CoffeeJUG. It's our first attempt to do an online version of our meetup. We have and actually had a lot of problems to do this. However, I hope that everyone can hear me very well, and as well he will hear our speakers. So why do we do this, and what is our main goal? It's a community, of course, because we believe that only helping another to become better, to proceed better and be success is possible only to be success in community. So that's our goal, to build a healthy, strong and huge Java community in Lviv and hopefully in Ukraine as well. This is our 9th event, and we have 361 unique participants during our all events and our activities. All these events are done by our team, Ira, Igor, and me, of course, and our program committee, who always care about talk quality and which speakers select for the future meetups. We have our partners, Avenga. We thankfully for all this support that this company provides to us. And we have a community partner, JetBrains, and we will use and actually raffle out JetBrains licenses at the end, but not through the online conference. Please ask your questions and provide comments through YouTube, and then we will raffle out the licenses using those emails and those contacts who will fill the feedback form. So please stay with us and don't miss your chance to get the JetBrains license. Join us, follow us, and we are really happy to try to do this online with all of you. Actually, right now we are switching to our first speaker, Łukasz, so you will see him in a few seconds. Thank you for your attention.
And today I would like to tell you a story of superheroes and superpowers. You may be surprised because the topic says it should be about machine learning, but we really think that machine learning is a kind of superpower in computer science world. And every superpower has some kind of origins. In case of machine learning, it's math. That's why today we'd like to talk about machine learning, the bare math behind libraries. My name is Łukasz Gebel, and my friend who will help me today and run the presentation next week is Piotr. And we are both software engineers at TomTom, when we work in location and navigation services department, and there we build services that, for example, help people to dispatch the large number of car fleet in the most optimal way. But today we'll be talking about machine learning. So I will start with defining what is machine learning so we get the common view the big picture view at this computer science domain. Then I will move to the main part of the talk, the supervised learning. And of course, at the end, I'll be happy to answer your questions. So let's start with some simple definitions. The first one by Arthur Samuel, who is like one of the founding fathers of artificial intelligence. And according to him, machine learning is a field of study that gives our computers, our programs, the ability to learn without being explicitly programmed. And it means that probably when you use machine learning, or you would like to use machine learning, you cannot figure out the perfect old-style algorithm, the imperative-style algorithm. So you want to do all of this. If that something happens, then do something stuff. Instead, you want to make your program learn how to solve the problem. And in the picture, you can see that Mr. Arthur Samuel is playing checkers with a computer that was able how to learn how to play checkers by playing with human players. The next definition, much less formal, is by one of our lecturers. So when we were studying, we had this task to implement an intelligent method. So we asked our teacher, what does it mean that a method is intelligent? And he said that he considers every method that needs some kind of training as an intelligent or machine learning method. And he used this intuition that animals and usually people are considered to be intelligent, and we also need to train. We also need to master some skills to become better and better. And the same applies to machine learning in general. Of course, it's very easy to say, make your program learn or make your computer learn, but how to do it? So let's look at the supervised learning. Personally, I like to compare supervised learning to being taught by a teacher. So when you were at school and you were learning all of this difficult stuff like adding numbers, reading, recognizing different types of trees and so on, your teacher probably gave you some examples and correct answers for each example. Then you could use these examples to generalize the problems in your head and answer the questions that were never asked before, at least in the classroom. The same intuition applies to supervised learning. So, first of all, you need your student that will solve the problem. And in this case, it's mathematical model. Then, you need to build your data set that consists of examples and correct answer for each example. Then you need to show all of the examples to the model and check how it responds. After that, you need to adjust the model parameters to make it respond correctly. And that's the main intuition behind supervised learning. One of the biggest algorithm groups in the machine learning world are neural networks, and they have really vast number of applications from computer vision to data compression and many, many more. And interesting fact is that they were inspired by biological brain mechanisms. So let's look at the biological neuron. So here we've got dendrites, and electrical signals from different neurons go through dendrites to our neuron cell. Then in the neuron cell, these signals are summed up, and if the sum is bigger than given threshold, our neuron produces its own output, which goes through a single output called axon. This intuition was used to model an artificial neuron, which looks like this. So in artificial neuron, we've got inputs, which are real numbers, and they are parts of our examples, like pixels of an image. And every input has corresponding weight, which is also a real number. And now how such an artificial neuron works? So you need to multiply every input by its corresponding weight, sum it all up, and put the sum into an activation function. And the result of the activation function, which is a single real number, is an output of our neuron. Activation function may look like this. It's like a classical one, sigmoid. And this one simply maps our sum to the values from zeros to 1. The problem with neural network is that it's quite hard to understand them, at least at the very beginning. So we'd like to use simpler method to explain the supervised learning, the linear regression. So linear regression is quite simple method for modeling relationships between variables. So for example, if you'd like to know how house size relates to its price, or how voltage relates to electric current, you could use linear regression. And we also like to explain problems using real-life examples, but we really think that real life of superheroes are more interested than our lives. So we will use a superhero real-life problem. Okay, so let's ask ourselves a question. What defined a superhero? Piotr, do you have any ideas?
Maybe large ears.
Large ears.
Like Dumbo.
Dumbo, from Dumbo. So you can fly with them, or
Yeah, you can fly with them. You can, create cool wind when it's too hot.
and hear anything, yeah?
Yes.
Okay, that's fair enough. However, in my opinion, costume is quite important. That's because, okay, I agree that we shouldn't judge the book by its cover. However, when you look at this guy, who is like wannabe Thor, we can agree that he's not very reliable, as for a superhero at least, and probably his superpower is being super creative, but original Thor is much more better. He's reliable, he looks very strong, he has proper armor, hammer, and so on. So costume is quite important thing on our way to being popular superhero. So let's say that you have some amount of money and you'd like to invest it in your costume. And of course, you'd like to know if you will be popular or unpopular superhero. To do this, we did some serious scientific research, and we have found most published superheroes ever. So our data looks like this. These are our examples. So for every superhero, we've got a number of comic book issues in which they appeared, and then we checked on eBay how much you have to pay for the costumes, and that's the value X in dollars. Using this data, these examples, we'd like to predict that for a given amount of money, in how many comic book issues will appear as a wannabe superheroes. And we'd like to do it using linear regression, the supervised way. Okay, interesting fact is that the Invisible Woman costume costs over $100, and there are two options. Either it's a brilliant scam, or it's really good costume because I cannot see there anything, but we'll leave the decision for you. Okay, let's get back to the linear regression. So our model in linear regression is simple line equation that you probably know from the primary school. So we've got two parameters, theta 0 and theta 1, a variable x, which will be the number of comic book issues from our examples, and the result of our function f will be the number of comic book issues for a given costume price. So x is costume price, result is a number of comic book issues. Very simple function. Our data looks like this. These are our points, and our task is to find the line that fits it in the most optimal way. And we'll do it in a supervised way. Okay, so how to do it? First of all, we'll need an objective function. In our case, our objective function looks like this, and it's a sum. So we need to calculate a sum using every point from our dataset. And we need to calculate a value of our function for given point x and subtract an expected value, the number of comic book issue for this particular point. Then we need to square it and add to our overall sum. That's how we calculate the objective function. And objective function is needed to evaluate if our model responds correctly or not. So let's look at a particular example. What's the intuition behind this particular objective function? Let's say that for 1 point from our data set, our function f gives us the value 4. But we were expecting 2 because y is 2. So in our formula, we've got 4 minus 2, it's 2, 2 squared, it's 4. It means that we need to add 4 to our overall sum. For different point, our function may respond at 1, and we may expect at 1. In such case, we've got 1 minus 1, it's 0, 0 squared, it's still 0. We don't need to add anything to our objective function. And you see this intuition that the closer to 0, the better. If the prediction fits the expected value, it's 0. So to get the optimal theta parameters, the parameters of our line, we need to find minimum, we need to minimize the objective function to find the optimal theta parameters. And we will do it using the gradient descent algorithm. Gradient descent algorithm is one of the best algorithms. I would say it's a superhero in machine learning world. And it helps us to find the minimum of our objective function. It's a very simple iterative algorithm where we update our theta parameters according to these formulas. They may look quite intimidating, however, simply you need to subtract an alpha rate, which is a small real number, multiplied by a derivative of an objective function. And that's how we choose our optimal theta parameters, just by subtracting using this formula. But why we need derivatives, which is quite complex stuff? So the main idea behind derivative is that they gives us information how our function is changing. So if our function is increasing, the derivative will be positive, and if it's decreasing, the derivative will be negative. And let's visualize this problem. Let's say that we've got very simple objective function, which is a parabola, and it changes on an x-axis. We've got objective function with regards to values of theta that may change while we are changing it in the gradient descent, and the y-axis shows the value of the objective function. And now let's say that we calculate the derivative of this function at this point. Here the function is increasing. It means that the derivative will be positive. And in our formula, in our gradient descent formula, we've got minus alpha times positive derivative. Negative times positive give us negative value, and it means we need to subtract something from our theta. Subtracting means we need to go to the left. Here the function is still increasing, so in the next iteration we are still going to the left until we reach the minimum. On the other side, at this point, our function is decreasing, so the derivative will be negative. So we've got minus alpha times minus derivative. Negative times negative, it's positive value. It means that we need to add something to our theta. Adding means going to the right on x-axis. And the next iteration, we do the same until we reach the minimum. And that's the main idea behind gradient descent and supervised learning in this field. So it's like walking down the hill in the space of your objective function values until you reach the minimum, the local minimum or global minimum. That's the main crucial part, which can be projected to much more complex method later. Okay, so now let me solve this problem. I will use an octave, which is environment and like mathematical programming language. So here is the implementation of my objective function, the formula that I showed you before in octave. So here we've got this sum, and that's the function f. So we've got thetas multiplied by x, subtract the expected value y. That's how we do it in octave. Then I've got my gradient descent algorithm, which is a simple for loop. And here I update my thetas according to this formula. So I subtract alpha times implementation of derivative formula, which looks like this. And there's only one theta variable. However, it's vectorized form, so it's like a vector of two variables. So here we've got two thetas underneath. And in my main code, I load my costume data points. I extract x and y's from it. I initialize theta at 0, set alpha to 1/4, and I will run the gradient descent for 1000 iterations. And hopefully it should produce the optimal data values for this particular data. So let's run the code, and here are our optimal datas, but they are not very self-descriptive, so let me plot result. And here we've got our optimal line. Now we can use it. So let's say that I would like to invest $1,000 in my costume, and I can take my prediction, my function, and check that according to my examples data, I should appear in around 8,000 comic book issues for the costume. Okay, it's not a bad idea. And as you can see, we can also learn something maybe trivial but sad about human nature. So it looks like the more you pay, the more popular you are. That's probably why Batman is so popular. Okay, so I solved the first problem, and you have seen the linear regression supervised way. The problem with linear regression is that it's linear. So let's say that you'd like to split Marvel superheroes from DC superheroes. In ideal world, you could use linear methods because data would be very simple, and you could use linear regression, for example. However, in real world, data is much more complex, problems are very complex, and usually we cannot use linear regression or linear classifiers. And that's the part where neural networks come to the rescue. So, simple neural network consists of 3 layers. The first one, the input layer, the yellow neurons, they just pass the value of our examples to the blue neurons, which are in the hidden layer. And in blue neurons, we've got this sigmoid activation function. Then the output of hidden layer neurons goes as an input to the output layer. Here we've got the red neuron is the only one in the output layer. Of course, we can have it more. And the neurons from output layer produces the final output of our neural network. We also have green guys with this +1, and they are called biases. And they give our neural network some kind of flexibility while fitting to our solution space. That's the general idea behind biases. So now, how to train a neural network? So first of all, we need to randomly initialize every weight of every neuron in our neural network. That's the first step. Then we need to present example, and it's called feed forwarding. And it works like this. You need to take your first example, pass its parts to the first neuron, multiply by its weights, calculate the activation function, do the same for the second neuron, for the third one, and then take the outputs of the hidden layer neurons and put it as an input to the last neuron. And you do the same. You multiply the inputs by weights, calculate the activation function, and you get the final output of your neural network. Now you can compare this final output with the expected value from your example. Remember this error, because that's the difference between expected value and the output, so we can call it an error of your neural network. And now we need to correct this error. And we will use the same idea we used before, the gradient descent. So it's called backpropagation algorithm, because you need to take this error, put it backward through your network, and when you're doing it, you need to update every weight of every neuron using very simple formula that I showed you before for linear regression, but now you will use the derivative of the sigmoid function instead of our objective function that I showed you before. But the idea is the same, updating each weight of each neuron using the gradient descent and the calculated error. So we take the error, we push it backward through our network, and we update every weight of every neuron, just like we updated our datas. And we are doing it iteratively. Then our neuron weights are getting better and better and better until it responds our needs, and it can solve the problem. And that's how neural network learns. Okay, so as you can see, unfortunately, there is no magic behind neural networks. So it's like quite old idea about randomized optimization statistics. So there is no magic. And when we were studying, and we were quite cocky when we finally understood how neural networks and machine learning worked, but then one of our teachers came in and she said that, come on guys, it's just a randomized optimization. But still, we think it's very fancy and very useful and powerful method, and it's worth understanding how it works. Okay, so I told you that neural networks are capable of solving nonlinear problems. So please let me solve a nonlinear problem. And we've got costume. So every superhero needs a logo. And logos are usually nonlinear. So let me show you how to generate a superhero logo using a neural network. So I will get back to Octave and my neural network code. So our data will look like this. It's plot grid. It will be a simple grid of points, 2D points. So for every point, we've got coordinates x and y, and additionally, there is a label, 0 or 1. And I would like to make my neural network learn which points are labeled zeros and which points are ones. Then I will draw the zeros and ones with different colors, and I hope that we will see some result. So I will show you the data once more in such form. So x and y coordinates and a label, 1 or 0. Then let me show you my generate logo code. So here I load these points. I extract x and y, so I take the first column from my file, the second column, the y, and the third column, expected output, is the label, 0 or 1. I will train my neural network for 1000 iterations, so I will show all of these examples and update weights 1000 times, and I will use 200 hidden neurons in the second layer, and there will be only one output layer because we need to know if it's 1 or 0. If you'd like to code more labels, you could use more neurons in the output layer. Then I will run the training using this backpropagation algorithm. And then when the neural network will be trained, I will take the same input that I used during the training and put it to the already trained neural network, and it will generate labels for this data. And I will draw these values, draw these points with correct labels. So let me run the generate logo code. And now all of this gradient descent stuff and randomized optimization is happening in every iteration. That's why it takes some time. And in a moment we should have our neural network trained. It's already trained. So the core part of our trained neural network are weights. The proper weights are the brain of our neural network, we could say. So let me plot results. So I will plot data, put inputs, and predicted values. And yeah, here we go. So it turns out that our neural network learned how to distinguish points that are inside Batman curve from the points that are outside of it. So we can say that we generated Batman logo using neural network. Of course, it learned this way because that's how I prepared the points. So simply I labeled these points like this. Inside there were all the zeros, outside Batman curve we've got ones. But there are two problems. First of all, Batman logo is already taken. And the second one is that, I used the same data that I showed during the training. So neural network already seen this data before. So it's like answering for the question that you've seen before. It's not a big deal. So now I will show you how it behaves on a data that wasn't visible during the training process. So I prepared different data. It's called Flickr grid. And Flickr grid doesn't have labels. These are just points. And during this training process, we had only 600 points. And in this Flickr grid dataset, I prepared 25,000 points. So the probability that the point wasn't visible during the training process is very high. So I've got my generate true superhero logo code. I just load these points, extract x and y coordinates, and I use this already trained neural network to generate a label for every point. And then I will use these labels also to draw the results. So let's generate true superhero logo and let's plot it. As you can see, it's much faster because there is no training. So it's much more thick and yeah, like DC universe. And as you can see, we get like, I don't know, flying squirrel man logo or
an elephant with a short trunk, maybe?
Yeah.
Dumbo,
yeah, maybe. So what happened here? So as you can see, we don't get a perfect path anymore. So it doesn't work perfectly well on a data that wasn't seen during the training process. And that's generally how machine learning methods work. So probably they won't give you perfect answers, but they will give you the answers that are good enough because you cannot get the perfect ones. You cannot figure out the perfect algorithm for a problem. So sometimes like accuracy or precision around 70, 80, 90, 95% is good enough. So probably we could fix it a little bit. We could add data for wings to make it more round or have more data points here. So our bat would have these ears. There are some artifacts also. So maybe we could change the number of our neurons in neural network, choose different learning rate and so on. However, we'd like to show you that machine learning is not a perfect solution. It will solve complex problems, but you need to be aware that some kind of trade-off between perfect and what you can get. Okay, so I hope I proved that neural network can solve nonlinear problems, as this logo was quite nonlinear. And that was it for supervised learning. So let's summarize the talk. So first of all, I defined the machine learning, gave you the basic intuition what it is. Then I solved the costume problem using linear regression, but in a supervised learning way. So not the classical mathematical way, but using our data points and using supervised learning. And I introduced a gradient descent algorithm. And finally, I used this gradient descent algorithm idea in our neural network, and I explain how neural network can learn to solve problems by this example of generating superhero logo. And now call to action for you. So I would like to encourage you to sit at home and try to implement this linear regression or any different simple method or simple neural network in your favorite programming language. You don't have to use Octave or any particular technology. Just try to implement these mathematical formulas. It's really quite easy. It doesn't need to be really performant. Don't care about performance at all. Try to find some interesting data set or make up interesting data sets like we did for this costume data. Play with parameters and check how it works. Change things, check how it works, what changes when you change the parameter, what changes when you change the number of iterations the algorithm works. And this will give you a very good understanding and intuition when you will deal with much more complex method. So that's how I learned machine learning, and I think it was the best way to implement simple method using my favorite programming language. Don't care about technology, don't care about performance. Okay, so play with machine learning, become machine learning superhero, and project these simple ideas to more complex one. And then if you don't understand this much more complex math in very complex methods like deep learning, you will still have this basic intuition about gradient descent, and it is really used there, but maybe sometimes in more tricky way, but the idea stays the same. Okay, that's it. Here is the bibliography. You can download the code and presentation using this link. I will also put it in a moment on my Twitter, so you can download from there if you like. I encourage you to take a look in Coursera machine learning course. It's a really good one. It's for free, and there is also a set of exercises that will give you really good understanding of machine learning, supervised and unsupervised. There are also some interesting books for you if you're interested in. And that's it. Now I'll be happy to answer your questions. Thank you.
Okay, thank you, Łukasz. As we have a delay between our call and the actual video stream, let's wait a couple of seconds until people watch it till the end. So probably some question will be arised. So
Sure.
yeah,
So,
just a few seconds.
Switch back to the bibliography so people can capture the code and the presentation link.
Yeah, sure. And actually, we had 32 people who watching us. So
Great.
yeah, and actually,
That's right.
it's very similar like approach like we have in real events. So we usually have 60, 80, 100 registration, and half of them only attends the event.
Yeah.
So right now,
It's similar in JUG in our city.
Yeah, in Łódź, in Poland, it's very similar.
okay, I see that our participants already saw the last slide, and they arise thanks comments, but I don't see any questions. So let's
Okay,
wait
so
at least I
Okay.
don't know 15 seconds.
Okay.
Yeah.
If they come up with any questions regarding Łukasz part, we can answer them after my talk next week. Also.
Yeah. They can
Yeah.
also ask them on Twitter, and I'll be happy to answer them.
Okay, I see one question from Lev. Okay, I will read it. The first question: can you do something if you do not really trust the data? Like examples, you feed to your monster. So that's the first question.
So if you've got unreliable data, I think that the important part is to try to at least clean them up and filter them up. So for example, you can do some anomalies analysis. So for example, to put the points that are very different from each other. So some cleanup, some filtering may be helpful in such case. So that's the one idea. And of course, usually, and that I also did with my data, I need to do some normalization of my data, because neural networks works great on the values from 0 to 1s. So we need to normalize them and to have the values from the same ranges, I would say, because sometimes you've got like one example that has value around in the range of 100, and then you've got different example for millions. So it also can affect your neural networks and your machine learning algorithm. So normalization is very, very important part, as well as taking care of discrete values, because sometimes you have your data in domain of discrete values. It means, for example, you've got like something is red, yellow, blue, and green. So you naturally could number them like 1, 2, 3, 4, However, then you introduce some kind of distance between your labels, because now green is, for example, 1 and blue is 4. And in numeric world, in the world of numbers, there is a distance from 1 to 4, and there is no such distance between blue and green in real. It doesn't need to be. So you need to be careful how you label your data, how you filter them, and how you normalize them. And that's also a big topic, how to prepare your data to make it useful for your machine learning algorithm.
Yeah, I totally agree. Actually, that's data science, right? It's called data science.
Yeah.
Okay, the next question is from Nick, and the question is, what are the practical limits of data sets? What kind of data sets can be used? Actually, how do you train for image recognition?
Yeah, so to be honest, I think in very popular and very effective deep learning methods, now it's hard to find really boundaries for data sets. They can be huge, and the bigger they are, the better in these deep learning methods. In past, for the simple method like I showed you before, you couldn't get very huge data because you could get overtrained, or the training would last so long that you won't get any results. But now with the deep learning methods, the bigger amount of data you have, the better. And these methods will deal with them very good. And of course, you still need to have a proper infrastructure, a proper, for example, cloud environment to process all of it, because you cannot do it on your laptop as you could before with the simplest method. But if you really need good performance, really good results, the deep learning and high number of examples, really high number like gigabytes or terabytes, is the way to go for you. It depends how much you can spend on your model and on processing. Does it answer the question, or there was some second part that I missed?
No, I guess so, but due to delay, we at least need to wait a little bit.
Yeah, sure.
If any other question still maybe arise, please don't hesitate to type them. If not, after 15 seconds, we will switch to maintenance screen, and I will continue our closing ceremony. So please don't drop the stream. Okay, I see that Nick confirmed that answer was actually question was answered. So, and no other questions. Then we will switch for a few seconds to the closing ceremony. Thank you again.
Yeah, thank you very much, guys. And I hope in the future we will meet in person. So stay strong.
Thank you. Okay. Hi everyone again. Sorry for this small delay. All the Skype translation is not very good. However, yeah, thank you, Łukasz, for your presentation, for your talk. It was very useful. I see the comments that everyone is happy. We had a max 32, 33 people watching us. So thank you so much again. And actually, I want to recall everyone that in 1 week, April 30, we will have a Piotr talk. It's his part related to unsupervised learning. So stay with us, follow us. It would be interesting. And once again, thank you, Łukasz. It was really interesting. You did it very well. Thank you. I hope everyone enjoyed. So thank you to our partner, thank you Avenga for their support of CoffeeJUG community, Lviv's community in general. Thank you again. According to our JetBrains licenses, we will raffle out them through the feedback form. So we will send it to everyone who watched our stream. Please try to give your feedback. It's very useful for us, at least because it's our first time when we're trying to do this online. I'm pretty sure you have something to say us. Feel free to do this through the feedback form. So thank you everyone. Thank you our speakers. Thank you our participants. Join us through all these channels, Facebook, Twitter and Instagram. And stay safe, stay healthy, stay at home, at least until this quarantine time. Have a nice evening. See you in 1 week. Bye-bye.